So today we are going to start with example number 6.7, which is a wheel with 10 metallic spokes, each 0.5 meter long, is rotated with a speed of 120 revolution per minute in a plane normal to the horizontal component of Earth's magnetic field HE at a place. If HE is equals to 0.4 G at the place, what is the induced EMF between the axle and the rim of the wheel? Note that 1 G is equals to 10 raised to minus 4 Tesla. So induced EMF is half omega B R square. सबकी वैल्यू रख देंगे. So we are having 6.28 into 10 raised to minus 5 volt. The number of spokes is immaterial because the EMF across the spokes are in parallel. Next is energy consideration or quantitative study. In section 6.5 we discuss qualitatively that Lenz's law is consistent with the law of conservation of energy. Now we shall explore this aspect further with a concrete example. Let R be the resistance of movable arm PQ of the rectangular conductor shown in figure 6.10. We assume that the remaining arms QR, RS and SP have negligible resistance compared to R. Thus, the overall resistance of the rectangular loop is R, and this does not change as PQ is moved. The current I in the loop is I is equals to sigma upon R, that is B LV divided by R. On account of the presence of the magnetic field, there will be a force on the arm PQ. This force I is I into 1 plus 1 into B is directed outwards in the direction opposite to the velocity of the rod. The magnitude of this force is F is equals to ILB is equals to B square L square V divided by R. Where we have used equation 6.7, note that this force arises due to drift velocity of charges along the road and the consequent Lorentz force acting on them. Alternatively, the arm PQ is being pushed with a constant speed V. The power required to do this is P is equals to Fv is equals to B square L square V square divided by R. The agent that does this work is mechanical. Where does this mechanical energy go? The answer is it is dissipated as joule heat and is given by Pj is equals to I square R is equals to BLV upon R square R into bracket whole square into R is equals to B square L square V square divided by R, which is identical to equation 6.8. Thus, mechanical energy which was needed to move the arm PQ is converted into electrical energy and then the thermal energy. There is an interesting relationship between the charge flow through the circuit and the change in the magnetic flux. From Faraday's law, we have learned that the magnitude of this induced EMF is sigma is equals to d phi b divided by delta t. However, sigma is equals to IR is equals to delta q divided by delta t into R. Thus, delta q is equals to delta phi b divided by R. Example number 6.8 is refer the figure. The arm PQ of the rectangular conductor is moved from x is equals to 0 outwards. The uniform magnetic field is perpendicular to the plane and extends from x is equals to 0 to x is equals to b and is 0 for x greater than b. Only the arm PQ possesses substantial resistance R. Consider the situation when the arm PQ is pulled outwards from x is equals to 0 to x is equals to b, and this is then moved back to x is equals to 0 with a constant speed v. Obtain expression for the flux, the induced EMF and the force necessary to pull the arm and the power dissipated as joule heat. Sketch the variation of these quantities with distance. So here we are having the figure. So let us first consider the forward motion from x is equals to 0 to x is equals to 2b. The flux phi b linked with the circuit SPQR is Q phi b is equals to BLX is equals to BLB. The induced EMF is sigma is equals to minus d phi by dt is equals to minus BLV, it is equals to 0. When the induced EMF is non-zero, the current I is in magnitude, I is equals to BLV divided by R. So here we are having the figure which is outward and inward for different values of x. The force required to keep the arm PQ in constant motion is ILB. Its direction is to be left in the magnitude F is equals to B square L square V divided by R is equals to 0. The joule heating loss is PJ is equals to I square R is equals to B square L square V square divided by R when 0 is less than or equals to X less than B, and 0 if B is less than or equals to X less than or equals to 2B. One obtains similar expression for the inward motion from x is equals to 2b to x is equals to 0. One can appreciate the whole process by examining the sketch of various quantities displayed in figure number 6.12b. Next is 6.8 ED currents. So far we have studied the electric currents induced in well-defined paths in indicators like circular loops, even when bulk pieces of conductors are subjected to changing magnetic flux. Induced currents are produced in them, however, that flow patterns resemble swirling eddies in water. This effect was discovered by physicist Foucault, and these currents are called ED currents. Consider the apparatus as shown in figure. A copper plate is allowed to swing like a simple pendulum between the pole pieces of strong magnet. It is found that the motion is damped, and in little while the plate comes to a halt in the magnetic field. We can explain this phenomenon on the basis of the electromagnetic induction. Magnetic flux associated with plate keeps on changing as the plate moves in and out of the region between magnetic poles. The flux change induce ED currents in the plate. Directions of ED currents are opposite when the plate swings into region between the poles and when it swings out of the region. If rectangular slots are made in copper plate as shown in figure, area available to the flow of ED currents is less. Thus, the pendulum plate with holes or slots reduce electromagnetic damping and the plate swings more freely. Note that the magnetic moments of induced currents depend upon the area enclosed by the currents. M is equals to IA. This fact is helpful in reducing ED currents in the metallic cores of transformers, electric motors and other such devices in which a coil is to be wound over metallic core. ED currents are undesirable since they heat up the core and dissipate electrical energy in the form of heat. ED currents are minimized by using laminations of metal to make a metal core. The laminations are separated by an insulating material like lacquer. The plane of lamination must be arranged parallel to the magnetic field so that they cut across the ED current paths. This arrangement reduces the strength of ED currents. Since dissipation of electric energy into heat depends on the square of the strength of electric current, heat loss is substantially reduced. ED currents are used to advantage in certain applications like magnetic braking in trains. Strong electromagnets are situated above the rails in some electrical powered trains. When the electromagnets are activated, the ED currents induced in the rails oppose the motion of the train as there are no mechanical linkages. The braking effect is smooth. Electromagnetic damping. Certain galvanometers have a fixed core made of non-magnetic metallic material. When the coil oscillates, the ED currents generated in the core opposes the motion and bring the coil to rest quickly. Third is induction furnace. Induction furnace can be used to produce high temperatures and can be utilized to prepare alloys. By melting the constituent metals, a high frequency alternating current is passed through a coil which surrounds the metals to be melted. The eddy currents generated in the metals produce high temperatures sufficient to melt it. Electric power meters. The shiny metal disc in electric power meter rotates due to the eddy currents. Electric currents are induced in the disc by magnetic fields produced by sinusoidal varying currents in a coil. You can observe the rotating shiny disc in the power meter of your house. This is the about electromagnetic dumping. Take two hollow, thin cylindrical pipes of equal internal diameter made of aluminum and PVC respectively. Fix them vertically with clamps on retro stand. Take a small cylindrical magnet having diameter slightly smaller than the inner diameter of the pipes and drop it through each pipe in such a way that the magnet does not touch the sides of the pipes during its fall. You will observe that the magnet dropped through the PVC pipe takes the same time to come out of the pipe as it would take when dropped through the same height without the pipe. Note the time it takes come out of the pipe in each case. You will see that the magnet takes much longer time in case of aluminum pipe. Why is it so? It is due to the eddy currents that are generated in the aluminum pipe which opposes the change in magnetic flux. That is the motion of magnet. The retarding force due to the eddy currents inhibits the motion of the magnets. Such phenomena are referred to as electromagnetic damping. Note that the eddy currents are not generated in PVC pipe as its material is an insulator whereas aluminum is a conductor. Next is inductance. An electric current can be induced in a coil by flux change produced by another coil in its vicinity or flux change produced by the same coil. These two situations are described separately in the next two subsections. However, in both the cases, the flux through a coil is proportional to the current, that is, phi B is directly proportional to I. Further, if the geometry of the coil does not vary with the time, then d phi by dt is directly proportional to di by dt. For a closely wound coil of n turns, the same magnetic flux is linked with all the turns. When the flux phi b through the coil changes, each turn contributes to the induced EMF. Therefore, a term called flux linkage is used, which is equal to n phi b for a closely wound coil. In such a case, n phi by is directly proportional to Y. The constant of proportionality in this relation is called inductance. We shall see that the inductance depends only on the geometry of the coil and intrinsic material properties. This aspect is akin to capacitance, which for a parallel plate capacitor depends on the plate area and plate separation and the dielectric constant K of the intervening medium. Inductance is a scalar quantity. It has the dimension of m, L2, T minus 2, A minus 2 given by the dimensions of flux divided by the dimensions of current. The SI unit of inductance is Henry and is denoted by H. It is named in honor of Joseph Henry, who discovered electromagnetic induction in USA, independently of Faraday in England. Mutual inductance. Consider figure 6.15, which shows two long coaxial solenoids, each of length L. We denote the radius of the inner solenoid S1 by R1 and the number of turns per unit length by N1. The corresponding quantities for the outer solenoid S2 are R2 and N2 respectively. Let N1 and N2 be the total number of turns of coils S1 and S2 respectively. When a current I2 is set up through S2, it in turn sets up a magnetic flux through S1. Let us denote it phi 1. The corresponding flux linkage with solenoid S1 is N M1 is equals to M12 I2. M12 is called the mutual inductance of solenoid S1 with respect to solenoid S2. It is also referred to as the coefficient of mutual induction. For the simple coaxial solenoids, it is possible to calculate M12. The magnetic field due to the current I2 in S2 is nu 0 N2 I2. The resulting flux linkage with coil S1 is N1 is equals to N1L pi R1 square nu 0 N2 I2, where N1L is the total number of turns in solenoid S1 and M12 is equals to nu 0 N1 N2 pi R1 square L. Note that we neglected the age effects of the and consider the magnetic field nu 0 N2 I2 to be uniform throughout the length and width of the solenoid S2. This is a good approximation, keeping in mind that the solenoid is long, implying I is much greater than R2. We now consider the reverse case. A current I1 is passed through the solenoid S1 and the flux linkage with coil S2, that is N2 phi 2 is equals to M21 I1. M21 is called mutual inductance of solenoid S2 with respect to solenoid S1. The flux due to the current I1 in S1 can be assumed to be confined solely inside S1 since the solenoids are very long. Thus, flux linkage with solenoid S2 is N2 phi 2 is equals to N2L pi R1 square nu 0 N1 I1. Okay, so we will just stop here. In the next video we are going to continue with electromagnetic induction further. Thank you.